Okay, so today we're starting one of the last chapters of this course, which is about factoring. So a lot of this class has been about kind of how do we put things together, simplify expressions, solve equations, and kind of the next step in advancing our knowledge of this language of algebra is to be able to break things down. So in the same way of like if you had a conjunction in English like can't, we know this is really the product of putting together can and not. And so that understanding is meaningful, right? To know that this is two things put together. And so it is that we spent all this time multiplying, adding, using exponents, using brackets to build, but simplify and reduce things down. Now let's say we have a result. What are the components of this result? So we're going to be asking the question, what was multiplied to get me? And there's different techniques to make this process a little bit easier, and we're going to learn those. But really the fundamental question is, right, what are the building blocks, like here, can and not, that give us this conjoined statement? If you just showed someone who is new to English the word can't, they might not know what that means, but can and not are more fundamental things. So without beating that analogy at all heck, let's jump in and work through an example. So we're going to start simple. What we're typically looking to do is rewrite things as a product of factors. And just to remind you, a product is the word that we use to describe multiplication happening, right? So rewrite something as multiplication of the parts of multiplication, factors. Okay. So again, we're asking the question, what was multiplied to get me? And sometimes it's a little bit nebulous because you can have different choices of factors. So if we just look at this 18x squared, we could think, what was multiplied to get me? Well, what are the different ways we could break this up? Well, we know that 18 can be written as multiplication of factors, right? We could write it as like 2 times 9 times x squared, right? That would be one way to write this. I could also write it as 2 times 3 because 9 is really 3 times 3. And I could break it down a little further. And I can't break these down anymore because these are what we call prime numbers, right? Remember, prime numbers means they have no other factors besides 1 in itself. So 2 times 3 is like the simplest way or the most broken down way that you can break apart 18. And for this x squared piece, what's the most broken down way I could write this? Well, times x, that's what that really means. Right? So it's like you've got this stack of Legos, and what you're trying to do is just figure out what kind of Lego pieces do you have. Right? Trying to break them all into the different components. And sometimes it might be, we don't need to break it all the way down. It depends on the context. It depends on what we're looking for. But this is just a first example of what I mean when I say breaking something down is factorizing it. What was multiplied to get me? Well, any kind of combination of these Lego blocks, right? When I put them, smash them back together and simplify it, we get 18x squared. So how about if we have this, let me get rid of this bullet point here. Okay, so what if we have this expression here, 2x plus 4? The question is still, what was multiplied to get me? What are the fundamental pieces that make this up? And again, why would we care about this? Oftentimes knowing what Lego pieces you have or what the components of a thing are help us answer or ask more interesting questions about the formula itself, about the model we're working with, the function, whatever it is. So what was multiplied to get 2x plus 4? Well, since we have this plus, we have to assume that this came from something distributing over addition, right? Remember that property of A times B plus C equals a times b plus a times c, right? We distribute that factor in. This must be the result of that. That's the only way we could multiply something together and still have addition in the middle of two terms, right? So if you remember, like negative 3 times like 2 minus x, what did we get here? This is a little bit goofy. If we had negative 3 times 2 minus x, just to give us a real concrete example, what happened here? This was negative 3 times negative 2, or negative 3 times positive 2, sorry. Negative 3 times a negative x gives us a positive 3x, and then we get a negative 6 plus 3x, right? So what we have here is we have this end result where it's been simplified, and we're asking, can we go the other direction to figure out where this came from? So one way that we do that is we do this process on each of the terms and see what was multiplied or what was distributed to get me, right? Because distribution is multiplication over addition, since this was here. So what we can do is we can rewrite this as simplified as each term can get, right? This was one term and we broke it apart. Break each term apart. So 2 times x, that's as simple as it gets. How about 4? I could factorize it as 1 times 4, but I could also write it as 2 times 2. And why would we do that? Well, because we can see that here, each of these terms has a common factor of 2. So it almost looks like this was distributed in from the outside to each term, and that'd be right. So let me copy that down here. So just seeing these be broken apart, now I can see, oh, this has a 2 that was distributed, and now I can pull this outside, and what we'll see is that 2 times what's remaining on the inside, x plus 2. This is factored form. So this is where it came from. This answers the question, what was distributed to get me, or what was multiplied to get me? This is what we must have started with, right? Because 2 times x plus 2 is 2x plus 2 times 2, which is 2x plus 4. Okay, so this can feel a little confusing at times because we are going backwards on the process that we've done before. So you got to really ask yourself, what is the purpose of what I'm doing? With factoring questions, we're looking to find what are the components that made this thing up. So I say that just because sometimes people will solve this and then redistribute like I did down here and think that this was part of the problem. This is really just checking to make sure what we did was correct. All right, so this is really the check. All right, so let's look at one that's a little bit more involved here. So let's say I had 6x squared plus 3x. So the question is, let's factor this, which means what we said above, right? What was multiplied or what was distributed to get me? So in order to do that, we got to do a little bit of sleuthing and break out each term into its most simplified, or not simplified, but its most simple factors. So that first one we could break into 2 times 3 times x, and that 3x is really just a 3 times x. That's as good as that one gets. And you know, you could write a factor of 1, but a factor of 1 is what we call trivial. It doesn't really add anything because you can multiply anything by 1 and get itself. So we're looking for non-1 factors. And then we see, okay, this is what each of these things have as a building block. So what do we see in common? Well, a 3 must have been distributed, right? In kind of our backwards engineering of this problem. 3 must have been distributed. They also both have an x. So an x could have been distributed as well. So it looks like altogether what must have been distributed was a 3x, and then whatever's left inside must have been what was there to receive it, right? To receive a factor of 3x. So what's left over? We got a 2 times an x, so a 2x plus, now here we go, is this 0? What are we left with? Well, if this were 0, let's chase down that idea. If this were 0, I'll go over here to thought experiment land. Oops. Because this is a good question, and it's one I get a lot. Maybe it'll let me. Here we go. Let's go over to thought experiment land. And this is worth writing down, just so you can show your brain why this doesn't work. So let's say that I said it was 0. It's not. Okay. But let's say that it was. Then if I rewrote this, 2x plus 0 is just 2x, right? So I get 3x times what's left inside, 2x. So if I said that this is the factored version of this, and I go to reconstitute it, right, put the pieces back together, what do I get? I get 6x squared, but I'm missing that second term, right? Where the heck is this 3x? And that is exactly why this is not 0 here. There must have been something here to receive a factor of 3x and then be equal to 3x afterwards. So what's that? If I multiply something by a number and we get that number, I multiply something by 3x and I get back 3x, that must be a 1, right? Because 3x times 2x plus 1, when I distribute that through, I get here 6x squared plus 3x times a positive 1 gives me 3x, and I'm back, right? So if you factor out in the common factor, all the component pieces take up all of the factors of one of the terms, then you're going to be left with a 1 on the inside. So that's a key skill there. Okay. And again, you can check yourself by redistributing, but really what we're looking for is this broken up form. Okay. So we'll do one more like this, and then we'll take a look at factoring by grouping, which is a little bit more involved, but exactly the same principle. And that's what I'm always going to drive you back to. This is always the same thing. The techniques might seem different, but it's all pointing to the same thing, which is we're just breaking stuff into its Lego pieces. Okay, so we're being asked to factor something with 3 terms, and you notice how I'm noticing that right out front, that I have 3 terms. So if I'm factoring something, it must have been the case that what? That we distributed something to a 3-term expression, right? Because we have to distribute over the plus and over the minus. So whatever it was, it must have been something times something with 3 terms, right? Now you can write it like that. It's fine. It's not necessary though. So it's just kind of like a frame for what we're up to. So similarly to before, we're going to break it into its pieces. So for each one, going through and breaking it apart as best we can. So 18a squared bc. What does this look like? Well, we could write this as 2 times 3 times 3, right? That would be fine. We could also notice something right up front when we look at the number parts, that they all have a common factor of 6. If you notice that, good. If not, good. Doesn't matter. So you can do this in an iterated way, meaning you can repeat this process until you're totally done. So you don't have to get it all on the first shot. But anyway, if you notice that they're all multiples of 6, then what you can do is say, well, this first one is 3 times 6 for 18. And then the numerical part, right, I've got A, B, C. And then, so that's totally broken apart. And then we can go to the next one, right? So 24 is 4 times 6. So that's plus 4 times 6. I've got an A term. Again, you don't need a million colors, so I'm just doing this for us here. And then C squared, CC. And then the last one, we've got negative 6 times 1. Right? You can write in the 1 if you want. You don't have to. Just like we said before, you're just going to get what you're left with. So A times A, B, and then 2 C's. So now the question is, what was distributed? Right? What was distributed? And I'm kind of flying through these breaking aparts here, but it might take you some time doing these when we're getting started. So don't, give yourself a hard time for taking your time here. Go slow, do it the right way, make sure it makes sense. Always, always. So the question is, what was distributed? Well, we see that since they all had a common factor of 6, a 6 must have been distributed into a 3-term expression. All right, so I know that 6 is a part of it. What else do they all share? What were they all given? Well, they were all given at least one A. Why at least one and not 2? This term only has one A, the others have 2. So we couldn't have said that they were all given 2 factors of A, right? They're all given 1 factor of A. In the same logic, they were all given 1 factor of B. This one had 2, but the others just have 1. So they were all given 1. And then same for C, right? This one was given 1C. This one must have been given 1 and 1. The others were there to begin with, right? So what we're seeing, what was distributed by what was circled. So it's 6, A, B, C. And then whatever's inside must have been what was there to receive these gifts of 6ABC, right? So this is equal to 6ABC times whatever was there. 3 times A was that first term, plus what was here? 4 times B times C. Make sure everything's kind of accounted for here, so 4BC. Minus, what was here? A 1AC, so we could just write this as AC on the inside. And that's what we call totally factored. And the reason is because you can take a look at each of these terms and you see, hey, they don't share anything, right? There's nothing that all 3 of them have in common anymore. If one has one thing, the other 2 don't have it, right? So this is totally factored, and again, you can check by just distributing that through. And since this is a 3-termer, let's go ahead and do that just to practice again. We'll do it quickly. Distribute this whole thing in and see, we should end up what you started with. That's what we're checking. So 6 times 3 gives us 18. A times A gives us A squared, and then BC. Second term, 6 times a positive 4 gives us plus 24. A, B times B gives me B squared, C times C gives me C squared. And then 6 times a negative 1 gives me a minus 6. A times A gives me A squared. There's no B here, so that's just B. C times C gives me C squared. And we ask, is that what we started with? It sure is. So we're good. Okay, so we know that we did it correctly. We don't have to be uncertain of our result. Since you broke it apart, you know how it should look when it's finished, right? Or you know how it should look when you recombine it or reconstitute it. Okay, so we're breaking things into their ingredients. We're breaking things into their Lego blocks. So this is how we would, what we call greatest common factoring. We call it the GCF because we're taking out what they share in the greatest fashion, right? Greatest common factor. I want to show you, just in case you didn't see what the GCF was with something. Let's say, one more example. let's say you didn't see it. The 6 above. So let's start with the same thing we had. AB squared C squared minus 6A squared B squared. So let's say you didn't see that there was a factor of 6, but I saw that they were all divisible by 2 because they're all even. If I just pull out a 2 and start with that, because maybe it's a lot to handle, minus 3A squared B C squared. I took out a factor that I knew that was obvious, and that actually helps me because now I look inside and I might see, hey, these are all divisible by 3 as well. What if I bring out a 3? What would that look like? Well, 2 times 3 leaves me with 3A squared BC plus 4AB squared C squared minus 1A squared BC squared. And so you see here now I have that 6, that 2 times 3, waiting for me. And then you can go through and maybe deal with the variables, right? Okay, I see there's an A, so I'm going to pull out an A. So I got 2 times 3, let's just call that 6A. And what am I left with in here? Right, and so I know I've pulled out all the A's I can pull out. Now I can go through with B and C and carry that through. And you should obviously end up with 6ABC times what we had on the inside for the same example, just to show you that you can do it in pieces. You don't have to do it all at once like we did up top. So with that, I'm going to leave this technique behind. I want you to jump in and practice this right away. And we'll go into the next kind of technique, which is if you have something with 4 terms, to start looking at what we call factoring by grouping. Okay, so here we have a 4-term expression, and we're going to use a different technique called factoring by grouping, because if you take a look, I could factor out a greatest common factor of 2, but this could actually go a little bit further. So I'll show how you do that if you just went with the GCF route and you wanted to do it in pieces. But in general, trying factoring by grouping is a good idea. What I mean is by looking at a group of 2 terms as kind of one thing that can be factored, right? So instead of thinking about what was distributed to 4 terms, think about the first 2 terms and say, what must have been distributed here? So what must have been distributed here? So we'll do a GCF method here. And we see, well, this is 2x cubed, so that's 2xxx minus 4 is just 2 times 2xx, right? And so what could have been the thing that was distributed here? Well, it looks like 2xx, or 2x squared, right? 2 and 2 x's. And so what we must have been left with was an x minus 2. So this must have been 2x squared times x minus 2. And for yourself, check and see what I did was correct there. Okay, so that's just for this kind of first part, this first group. For the second group, we can do the same thing. And, right, what was distributed here? Well, you could rewrite this as 10x minus 2 times 10 is 20. Again, if you saw that GCF, you could do it in parts like we saw just before, if you didn't see that. But we see, okay, both of these got a 10, and that's about it, right? And what we're left with on the inside is x minus 2. I'm actually going to swap my color so we don't get confused here. So we have a common factor of 10, and what was left on the inside was x minus 2, right? So we're left with plus 10 times x minus 2. So again, this was what this must have came from. And now that we're here, we can kind of drop the thought bubbles of considering them separately, because it really is one expression, right? So this is 2x squared times x minus 2 plus 10 times x minus 2. And so you might look at this and say, man, this doesn't seem much better, but it really is. And the reason is, if you think about it, this has a common factor that's been distributed from something else, right? Both of these have a number x minus 2 that's been multiplied in. Our brain kind of plays a trick on us. We see x and 2, we think of them as separate numbers, but really, this x minus 2 is one number. So in other words, if we thought about it instead, if I showed you, hey, why don't you factor 2x squared times 5 plus 10 times 5? You'd say, well, that's easy. It's just we take that 5, that must have been what was distributed, and what was left inside was the 2x squared plus 10. Right, so that 5 is what must have been distributed through. It's the same thing here. It's just that it's not 5, it's x minus 2. So what must have been that number being multiplied was x minus 2, and what's left inside is 2x squared plus 10. So I want to pause here because this is this comes from a double-double, right? When we were double distributing before in chapter 1.4, we saw how distributing something in a 2-termer into a 2-termer resulted in a 4-termer. And that is good. This problem has an extra dimension to it. So on its face, though, this is how you would solve this problem. But what do we notice when we look at both of these factors? This one's pretty simple inside, right? This one here, though, both of these terms are divisible by 2. And so what we can do is go ahead and pull out that 2 to completely factorize it. So this would be, we could write this as 2 times x minus 2 times what must have been left inside here, right? If I pulled out a 2, it must have been x squared plus 5. So if we wanted to completely simplify it, that would be, or completely factor it, that would be the way to go. Okay, so when you're done factoring, or when you think you're done factoring, look at each of your components and say, is there a greatest common factor I could pull out of this? And you notice that this 2 was just a part of this, and now we're breaking it into those Lego pieces. So there must have been 3 Lego pieces to this from what we started with. Okay. So like I said at the beginning, you might have noticed that the 2 was a GCF to start. That's usually the best way to go. And I'll show you how you deal with that, because it can feel different, but it's really exactly the same, which is if we started with 2x cubed minus 4x squared plus 10x minus 20. Factor, let's say an alternative way. Alternative. So let's say you notice that 2 was a GCF. Then you can rewrite the inside like so. And then again you can do factoring by grouping, and it's going to follow the same way, right? We consider just here at first, but we've got to kind of carry this 2 along as sitting outside. So this became x squared times x minus 2. Right? And then this guy, 5x plus 10, this became plus 5 times x minus 2. And so we're kind of working within this walled off factorization. And again, we can pull out this x minus 2 must have been distributed, and so we end up with 2 times x minus 2 times what was left over, x squared plus 5 on the inside. So we'll get to the same place. Obviously each of these steps you would do it like we did up top, right? A little bit more thoroughly. Over time, we'll get faster. But for now, take your time. I'm just trying to go through these examples to show you the process. And hit rewind and pause as many times as you need and verify the steps that I'm doing. All right, so let's do one more example by grouping, and then we'll call it a day. Okay, so let's say for our last example, we've been asked to factor this thing here. Now, for right now, you might notice that the middle terms are like terms and could be combined. For the sake of this example, I'm going to say we don't want to do that. Factoring is really breaking things apart. It's not simplifying things. So since this is broken up in such a way, this is actually going to help us. Okay, so let's leave it as is and start to break this into pieces like we did before. So if it makes sense, look at this grouping here and see what must have been distributed. Well, it looks like a 3 must have been distributed. Right, because that would have left us with a 2 plus 1 something. An x must have been distributed, so maybe it was 3x times 2x plus 1. Double check that that makes sense. Right, so let's go ahead and do that. We'll factor this to be 3x times 2x plus 1. And then over here on this second set, second group, what must have been distributed here? Well, there's only one x here, so we know it will only be maybe in the number part. So it looks like both of them got a factor of 4, and not even a factor of 4, but a factor of -4, because they're both negative, right? So we could pull out a -4 and see what happens. So if I pull out a -4, what would I be left with? So minus 8x minus 4 equals -4 times, well, let's actually write it like this, one step in between. I could write -8 as -4 times 2x, and I could write -4 as -4 times 1 to clearly see I've got a factor of -4 that I can pull out, and what's left inside is 2x, and since I pulled out the negative, it's really a plus 1. Right, and if that didn't make sense, we pulled out the negative sign. This was distribution, so this has to have a plus sign in the middle. It can't just vanish, which I see happen sometimes. So it must have been plus if we're pulling out the negative. So it just changes the sign. And again, go backwards on this to make sure that makes sense to you. Meaning, distribute this through and see that you end up back where you started. So this should be -4 times 2x plus 1. And then what do we see? These things share a common factor of 2x plus 1. Only through doing it by groups would we have access to that. So we pull out that factor of 2x plus 1. And what were we left with? 3x minus 4. And so that's totally factored. So obviously this is a bit more involved, and it relies on you being pretty comfortable with the first types of problems we did. So make sure that you're comfortable with doing these GCF problems before moving towards the end of the section and doing the problems by grouping. Okay, so these are the first two kind of techniques, and they're both driving at the same thing, which is what? What was multiplied to get me? What were the component parts that we started with to end up with this simplified result? So have fun. We'll see you in the class discussion.